Last lecture we considered capacitors, and now we are going to consider inductors. Inductors are electromagnetic devices, and these devices could be modeled as wires wound into several loops to form coils. So whereas capacitors avoid an instantaneous change in voltage, inductors resist instantaneous change in current. Okay, we're going to see that shortly. So it means that they prevent an abrupt change in current. So here, if we see a ferromagnetic core, for instance, then we have it. Instance, let's say current through this. So this forms n-ton of coils. Okay, and then this forms a ferromagnetic core or ion. Same ion. Then right in here we have the flux. This is the flux. So we already know the reason an ion is used. It's because they are good conductor of magnetic flux. Okay. So the coil links the flux, this coil in red, links this flux n times relative to the number of coils, the n coils, okay? So that in this case, let's say flux linkage, say lambda becomes lambda equal to n. But we also know that the flux linkage is proportional to current. That is, lambda is proportional to current, the flux linkage. So that the flux linkage will now be the same as L, where L is the constant of proportionality. And this time, in this case, L is the inductance, which is usually measured in amps, right? Second, okay, which is equal, which is H. Now, you want to recall Faraday's law, okay? From Faraday's law, we know that the time varying magnetic field testimony based on convention, magnetic flux. Linking a coil will induce a voltage, right? That's the coil. So that V is the same as the lambda over the T, which is going to give us, now lambda is n phi, right? So that will be N, the flux, dt. Okay. So if we have this as N, the flux dt, so this is now going to give us lambda here, the lambda, that's Li, right? So that's going to give us the same as L, where lambda is Li, L, the I, dt. Okay, and we already know that Lenz's law mentioned that an induced voltage always gives rise to the current whose magnetic field opposes the change in the original magnetic flux, right? So now that we have this going, we can now provide the symbol for the inductor. Now, the symbol we have recorded. Okay. This is L, then we designate the voltage by the polarity and the magnitude V. We already know that voltage is the same as L, the I, the T, okay, based on Faraday's law. And for us to now evaluate the current from the voltage relationship, we know from this, if we cross multiply V dt is equal to L the I, right? Okay. So that the I is the same as 1 over L V dt. So integrate both sides. So 1 over L integral V dt. And then I will be the same as 1 over L integral V, let's say the tau or the T, so the tau here, plus L of naught. I'll know that L of naught is the initial current through the inductor. The inductor T, what is it? So from the voltage current relationship, we now see that when the current does not change smoothly, no voltage is created across the inductor, right? From this expression. So it means that we can only measure voltage across this inductor when the current changes smoothly over time, when it is continuous over time. So this also now derives the conclusion that an instantaneous change in current would create a single or one humongous voltage across the inductor. Okay, so instantaneous changes in current is allowed. Then the voltage current characteristics follows directly, so that the IV characteristic will be V equal to L di dt and L integral V the time plus I L. Okay. However, the energy stored. So let's look at the energy storage for the inductor. So we have R is the time rate of change of energy, right? So that the energy, the P, the T. This is going to give us some L of T, L of T, dt. Now, this will now give us, already know what the voltage value is. So that will be L, the I, the T, IL, and T dt. So this can cross this so that the energy, the W, will be the same as L, the I, L, the IL, then we also have IL, right? No, it's IL. So if we exclude the T, so where IL of T is equal to IL, okay? This is also T. Okay. So this is going to give us L, okay? No? Okay. So now that we have this, we can integrate both sides to be integral L, L, integral L. So we integrate this, that will give us the energy, right? The energy will now be L, I squared over 2, take 0 to I, right? So 0 to I. So this would be L, I squared over 2, 0 squared over 2. So the energy will be Li squared over 2, which is 1 Li squared. Okay, and this once again implies that the energy in the inductor is always positive, okay? Energy in the inductor is always positive. Okay, then some other interesting points to note is that the inductor absorbs power from the circuit when storing energy, and then the inductor releases the stored energy when delivering energy to the circuit. Also, you want to know that the inductor stores energy in the magnetic field, right? So inductors stores energy in the magnetic field. Okay, so same way we presented for the capacitor. So it means that magnetic energy stored the still store magnetic energy in the inductor. And then also inductors resist instantaneous changes in current. So how do we resolve the equivalent circuit for inductors? So let's consider series inductors. So we have inductors connected in series. So minus, this is V of t. So there's a current flowing through. It's L1, L2, L3. So plus minus V1 of t, plus minus V2 of t, plus minus V3 of t. And this is equivalent to plus minus V of t, for which we have the equivalent resistance. Now, since we have the same current flowing through and different voltage drops across each element, so Kirchhoff's voltage law applies. So that V of t will be the same as V1 of t plus V2 of t plus V3 of t. And that will give us L di t dt plus that's L1 plus L2 di of t dt plus L3 di t dt. L1 plus L2 plus L3 di T dt. So this is the equivalent resistance, which will be the same as L1 plus L2 plus L3 for series connected inductors. And then when we have inductors connected in parallel, so this is L1, L2, and L3. So we have I1 of T flowing through this branch, then I2 of T flowing through that branch, and then I3 of T flowing through this branch. So P of T, then what's going to be the equivalent inductance minus P of T. So we have T. So in this case, we have the same voltage applied across the parallel connected inductors, this parallel inductors. And then we have different currents, current values flowing through each of the elements connected in parallel. Now, Kirchhoff's current law applies, so that I of T will be the same as I1 of T plus I2 of T plus I3 of T in this case. So this is going to give us 1 over L1 integral V d tau plus A1 of naught plus 1 over L2 integral V d tau plus I2 of naught plus 1 over L3 integral V d tau plus I3 of naught. So here, collect like terms, 1 over L1 integral V d tau plus 1 over L2 integral V d tau plus 1 over L3 integral V d tau, auto as much as many elements we have, then plus I1 of naught plus I2 of naught, which are the initial values at t equal to 0, plus I3 of naught. Okay, all the way. So this is going to give us I1 over L1 plus 1 over L2 plus 1 over L3 all the way. So for the nth inductor times integral V d tau plus I1 of naught plus I2 of naught plus I3 of naught. And this is the equivalent inductance. So that this will be 1 over L equivalent. So that 1 over L equivalent will be 1 over L1 plus 1 over L2, 1 over L3 all the